This video will discuss atomic number, mass number, and isotopes. So what makes one element different from any other element? What gives an element its identity? Well, if we focus on boron, for example. So boron's element box has two numbers. The whole number, wherever it may be, is what we call the atomic number. The atomic number is what gives identity to the element. The atomic number, despite what you may have been taught before, is the number of protons within the nucleus. So if we have 5 protons, it can only be boron. As soon as we add another proton, it becomes carbon. If we take away a proton, it becomes beryllium. So the number of electrons can differ, but that does not change your element. The number of neutrons can differ. That does not change your element. But the number of protons defines your element. So that's how we tell. We look at the atomic number. So what is this number? Well, if we take a look at boron, we know one atom of boron will have 5 protons. That's its identity. And we know protons are positive. In this chapter, and this chapter only, well, we always assume we're dealing with neutral atoms. They have no charge. Well, if we have 5 positives, well, we need 5 negatives. So in this chapter, the number of protons, unless you're told otherwise, will also be the number of electrons. But remember, Rutherford discovered that the mass of the atom is in the nuclei. So we know the electrons matter, but they're so tiny in their masses that they don't significantly add anything to the mass of the atom. If we take the number that has digits after the decimal place and round this to the whole number, it is called mass number or atomic mass. And of course, this number would be 11 for boron. We arbitrarily allow a proton to be assigned a value of 1 mass and a neutron a value of 1 mass. This is protons and neutrons, atomic mass. So if we take the atomic mass minus the atomic number, it is protons and neutrons subtracting away the number of protons. We get the number of neutrons. So for boron, 11 minus 5, we have 6 neutrons in the average atom of boron. All right, just for practice. How about potassium? Well, we know from the atomic number, there are 19 protons. If it is neutral, and we're not told otherwise, we'll have 19 electrons. The mass number would be 39. So the mass number, protons and neutrons, minus the number of protons, 20 neutrons for potassium. One more, bromine. Atomic number, this we would report as 80 as the mass number. 35 protons, 35 electrons, 80 minus 35, and we have 45 neutrons. Okay, so we've talked about atomic number, mass number. All right, but isotopes. Recall that John Dalton communicated in his atomic theory that all atoms of an element are identical in all properties. Well, since then, we found out otherwise. Every element has at least 2 versions of itself. Well, how can that be? How can we have different versions of an element? Well, those are isotopes. There are 3 forms of hydrogen. And one way we can represent isotopes is by taking the element symbol dash its mass number. One version of hydrogen is hydrogen 1, another version is hydrogen 2, another version is hydrogen 3. Again, these are mass numbers. So how can they differ? Let's examine their protons, electrons, and neutrons. Well, hydrogen 1, this is the mass number. Well, to be hydrogen, it has to have one proton. If it's 2, it's helium. If it's 3, it's lithium, and so on. If it's neutral, which we're not told otherwise, 1 electron. This is the mass number. Mass number minus atomic number is number of neutrons. So this version of hydrogen has 0 neutrons. Hydrogen 2. Well, to be hydrogen, we must have 1 proton. We're neutral. 2 minus 1 would be 1. And then going along with this version, again, it's hydrogen, so it has to have 1. It's neutral. So how do different versions of the same element differ? It's in their number of neutrons. So isotopes are different versions of the same element. So they will have identical atomic numbers. That's what gives identity. They differ in their mass number, or their number of neutrons. So to just show us some kind of diagrams of these, we actually have nicknames for them. We deal with hydrogen so often in research because of its abundance in water that we've actually nicknamed. You are not responsible for knowing these are the isotopes of hydrogen, but we call the first version protium, then deuterium, and then tritium. And this is, the prefixes are to match the mass numbers. So we can see that what they're showing is the protons as red and the neutrons as black. So it's the nuclei that differ by their number of neutrons. Now, all the isotopes are not found with equal likelihood. There are several different isotopes of carbon, but these are the most common. So we have carbon 12, carbon 13, and carbon 14. And we can see the percentages at which we encounter these. So if we have 100 atoms of carbon in our hand, almost 99% is carbon 12, and about 1% is carbon 13, and a minute fraction is carbon 14. I'd like to take the opportunity to also talk about, now we could, identify tritium as H-3, but we could also use what's called a nuclide symbol. A nuclide symbol is the element symbol. To the upper left is the mass number. To the bottom left is the atomic number. So a nuclide symbol, we have the element symbol. To the upper left is the mass number, or atomic mass. To the bottom left is the atomic number. And if your atom or element would be charged, you would show the charge as a superscript, as an exponent to the upper right. Since there is not one, we're assumed to be neutral. So the nuclide symbol for carbon 14 would be 14 mass number, and then of course to be carbon, atomic number is 6. All right, so that talks about what we were looking for this video.